So moving on to bond enthalpies, I'll go through now in the video what endothermic exothermic reactions are with respect to bond enthalpies, move then on to average bond enthalpy calculations, an idea of the definition and an understanding of how these average bond enthalpies are ascertained, and then furthermore on how to compare these to other values such as those related from Hess's cycle or those from data books. We'll then move the video on to Hess's law and enthalpy cycles and go through various calculations and relate them to exam style questions. So the discussion begins with first looking at this reaction. You may notice at the top of the page, methane reacting in the presence of plentiful oxygen to produce CO2 and H2O. Here the balanced equation represents, as you may have understood so far, the standard enthalpy of combustion of methane, 1 mole of methane burning in plentiful oxygen. What I've shown you are the displayed formulae for methane, for the O2 double bond, for the carbon-oxygen double bonds in CO2, and of course the bonds in H2O. This is simply to illustrate the concept of energy values. Now, effectively, these reactants, as we've understood in previous videos, these molecules have a certain amount of energy. They're vibrating, they're moving around. I've effectively illustrated that here. Here are the reactants, methane and oxygen, with an energy level displayed around here. The numbers aren't important. It's comparisons between what's about to happen. That's for you to understand. So, energy goes in to break bonds. So these bonds in the reactants have to be broken, and here you see all the atoms separated. I've tried to color code them so you can follow what's going on. So from the reactants, when they're joined together in their bonds, methane, oxygen molecules, energy's gone in, and that's caused bonds to break. Now, these atoms, you won't generally find these lying around. They must then want to reform other bonds. So now, in order to form the bonds of these products, so these bonds that are illustrated here, energy is released, allowing them to become more stable by becoming CO2 and these water H2O molecules. What I'd like you to appreciate, adding energy broke the bonds, causing the atoms, individual atoms, to be at a higher energy level, illustrated here. They then released energy to form these products. They, however, are at a lower energy level compared to the reactants. So overall, energy went in to break the bonds in these reactants. Energy then got released when reforming the bonds of these products. Energy's gone in, delta H is positive to break the bonds in reactants. Energy is released when reforming the bonds of the product. At the bottom here, I've tried to now illustrate this balance. First of all, this initial reaction we can relate to an earlier video where we looked at enthalpy profile diagrams. I haven't labeled the axes just to save a bit of space. Energy on the y-axis, progress of reaction on the x-axis, the level, energy level of the reactants illustrated here, energy level of my intermediate particles, i.e. this represents the activation energy. They then release energy to reform bonds of products, and the products have a lower energy level than the reactants. Overall energy went in, but more got released. So let's now look at the balance. Energy going in to break the bonds in the reactants, energy being released out when reforming the bonds in the products. If the energy going in is less than the energy coming out, it's an exothermic reaction. So in this case, the energy going in, that activation energy illustrated here, is less than the amount of energy that came out. The amount of energy that came out, that big fall, the energy going in was that initial rise. Overall, more energy is being released. The products end up at a lower energy level. It's an exothermic reaction. There are other examples we'll look at where the energy going in to break the bonds in the reactants is greater than the energy being released when reforming the bonds of the products. That would overall have been an endothermic reaction. Let me quickly illustrate that down here in the gap. So we see here, energy's gone in, the activation energy to break the bonds in the reactants, then some energy got released when reforming the bonds of the products. Overall, the products ended up with more energy than the reactants. The delta H was positive, as illustrated here. So this enthalpy profile diagram refers to an endothermic reaction. Energy going in to break the bonds in the reactants is greater than the energy being released when reforming the bonds of the products. This is an endothermic reaction illustrated in this enthalpy profile diagram. An example, for instance, could be the thermal decomposition of calcium carbonate. Energy goes in to break the bonds in reactants. Energy is released when reforming the bonds of the products. Overall, there's a positive delta H. It's an endothermic reaction. There are others, but this is one example I just wanted to illustrate now while we're addressing the point. So you now have on this page an exothermic reaction. Here I've actually mentioned it's minus 890 kilojoules per mole. This is the enthalpy profile diagram of the exothermic reaction, the combustion of methane. Energy going in is less than the energy coming out. Exothermic reaction. Endothermic, the opposite, energy going in is greater than the energy coming out. Energy going in is greater than the energy coming out. Products end up with more energy than the reactants. Endothermic reaction. Okay, moving on. Let's talk further about the definition. So when we now think of bond enthalpy, we're referring to the idea that you could take a bond, let's say hydrogen with a single bond between the two H's. If you break those bonds, a certain amount of energy must have gone in. Now, a single bond is fairly small. In fact, it's minute. However, if I had a mole of hydrogen molecules and I broke a mole of those bonds, I'd end up with 2 moles of these hydrogen atoms. Earlier lectures will illustrate what this mole concept is. I'm hoping all of you are familiar with the mole concept, so I won't dwell on it too long. And we could therefore measure the amount of energy going in to break 1 mole of these HH bonds to produce 2 moles of hydrogen atoms. However, similar concept, carbon-hydrogen bonds, I could break a mole of these. A certain amount of energy would have to go in to give me a mole of carbons and hydrogens that are now separated. But that value is not the same for every CH bond. So I could have, here are a few examples. Here's ethane, CH bonds, as you can see. This here, as you can see, is ethanol. And finally here, ethanoic acid. All of these examples have CH bonds. The value, the energy value, the strength of these CH bonds is different depending on the different environments. Therefore, when we look at bond enthalpy, we look at average bond enthalpy. So, the value for these bonds, the CH bond is 412 kilojoules per mole. 1 mole of these bonds breaking, whereas the average bond enthalpy for OH bonds, and again I've shown you 2 examples here where there are OH bonds, they individually have different strengths and values, but when we look at the average, it's 463 kilojoules per mole. Both of these are positive values because energy has to go in to break the bonds. And therefore we can now look at the definition for average bond enthalpy. The average energy required to break 1 mole of a bond, considering the bond in different environments in their gaseous state. A couple of things to note. First of all, average bond energy. Why? Because we're looking at that bond in many different environments. These are just 2 examples. There are loads of examples where there are CH or OH bonds, and therefore when we look at any particular example, we're looking at those bonds having considered many different environments. Whereas this H2, there is only 1 HH bond, and therefore its value is not necessarily an average. In your exams, you are going to be addressing calculations involving average bond enthalpies, where the average bond enthalpy is taking into consideration the strength of those bonds when looking at a mole of bonds in many different environments. Gaseous state. This is interesting as well. Some of these molecules, so ethanol, ethanoic acid, are liquids, and you're correct in saying that at standard state they are liquids, but we're concerned with breaking the bonds
when those molecules are in their gaseous state. So not the energy required to make them gases or from solids to become gases, etc. It's simply just when those bonds are in their gaseous state, the value, the strength, the average bond enthalpy for those bonds. Energy going in, positive value, the amount of energy required to break 1 mole of those bonds, considering they're already in the gaseous state, to simply make gaseous atoms. We're not concerned with reforming any solids or gases or reforming other compounds, simply just breaking a mole of bonds without worrying about changing state, no latent heat, etc. So keeping the conversation simple, bond enthalpy refers to energy going to break bonds. How much? 1 mole of bonds. Average bond enthalpy, very important question in exams, refers to the average energy required to break 1 mole of a bond, considering the bond in different environments in their gaseous state. So we can now look at an average bond enthalpy calculation. So the first example, I'm going to use the same from the other page, methane's combustion. Again, I'm showing you the displayed formulae to illustrate what we're about to do. Whenever you see an average bond enthalpy calculation, you have the reaction you're trying to work out. I prefer drawing a line down the middle under the arrow illustrating my reactants and products are separated. The value of each of these bonds are shown here. I'd now like you to have a go at this calculation, and then I'll go through the answer with you. So, give you a few seconds, you can pause the video, and then I'll go through the answer. Okay, let's go through the answer. So, here I'm showing you the number of bonds that are breaking, i.e. the energy going in to break 4 CH bonds, that's the ones of my methane, 2 O2 bonds. Now there are 2 O2s, therefore there would be 2 of these O2 molecules, 2 of these double bonds that are going to be broken. That's their value, which I've got from this list here. And likewise in my products, I'm reforming these bonds. So CO2 has 2 CO double bonds either side. If I have 1 CO2 molecule, I've got 2 of these bonds, as it's shown here, 2 times 805 kilojoules per mole. Likewise, my water molecule has OH bonds. Each molecule has 2, so if I have 2 H2Os, I must have 4 OH bonds. Simple calculation. Now revealing my answers. That becomes 1,652. 2 times 497 is 994. Add those two together. This is the energy going in. These calculations from these numbers give me this energy being released. Our calculation now is very simple. The delta H for this reaction, energy going in minus the energy being released, because that's a positive number, and this is a negative value, so hence we put a negative here. That minus that energy going in minus the energy coming out gives me my overall delta H minus 816 kilojoules per mole. Keep in mind what we said earlier about the balance of energy going in and out. Energy going in to break the bonds in the reactants, all of these bonds, is less than the energy coming out when reforming the bonds of my products, i.e. these here. Therefore, it's supposed to be exothermic, and yes, it is exothermic, straightforward balance. At this point, I'd like you now to focus on this number here. This is the actual enthalpy of combustion for methane. It's minus 890 kilojoules per mole. The discrepancy is obvious. Our average bond enthalpy calculation shows minus 816 kilojoules per mole. The question is why? I'll give you a few seconds to think about this before I go through the answer. So, hopefully you've had a chance to think, or pause the video and think. Effectively, it's important for exams to be able to justify why this difference occurs. This is a less accurate answer. This average bond enthalpy calculation refers to bonds and their values when looking at many different environments. Average bond enthalpy, the average energy required to break a mole of bonds when considering the bond in many different environments. So therefore, these values refer to breaking bonds, and of course these refer to making bonds when looking at those bonds in many different environments. hence this value is less accurate. This, however, is the actual value for the combustion of methane because it refers to the balance of energy going in and out, energy going in to break these bonds, energy coming out when reforming these, specific for just these compounds, just these molecules, just this reaction. So, energy going in to break methane and 2 oxygens, energy coming out to reform CO2 and 2H2O, the balance between them is this value. And therefore, this is the accurate value specific to the combustion of methane, whereas this value is, using average bond enthalpy calculations, it's fairly close. It gives you an idea of what's going on, but we have to keep in mind it's an average bond enthalpy calculation, not as accurate as the actual value, simply because it relies on data referring to bonds from many different environments. I hope that's clear. Now let's look at some examples. So I'd now like you to look at this particular example, read the question, I'll give you a few seconds, you can pause the video, and then I'll go through it myself. So pause the video now, and after a few seconds I'll go through the question and then reveal my answer. So, here we go. Here is the complete combustion of butan-1-ol. Butan-1-ol reacts in plentiful oxygen to release 4 CO2s and 5 H2Os. Use the following average bond enthalpy data to calculate the combustion enthalpy for butan-1-ol. So, these are the values for the different bonds in question. Have a go, look and see what you did compared to what I'm about to show you now. I've got my reaction here. I've put a line down the middle to separate my reactants and products. Altogether, I was breaking 3 carbon-carbon bonds. Here's a calculation. 9 carbon-hydrogen bonds. Here's a calculation as such. And 6 oxygen-oxygen double bonds. Here's the calculation. These numbers are coming from this table here. So, those are the values which I've added to give me that total. Finally, looking at the products, 4 CO2, so 8 C double bonded O's. I'm forming these 5 H2O, so altogether 10 OH bonds. I'm forming these. Again, these values have come from this table here. The total for that, these two added together, is that value. This is an exothermic value. My energy going in minus the energy coming out gives me the delta H, which is minus 3273 kilojoules per mole. An exothermic reaction, the energy going in was less than the energy coming out, energy going in to break the bonds in reactants, less than the energy coming out to reform the bonds of the products. Delta H is an exothermic value, 3273 kilojoules per mole. The question also wanted to know the value given in the data book for the combustion of butan-1-ol is minus 2670 kilojoules per mole, different to the value we've got, fairly significantly different. Why is the value we calculated above different to the value shown in the data book, which is here, a more accurate value? Because the average bond enthalpy calculation refers to the making and breaking of bonds when considering many different environments, whereas the data book value refers to the bonds made and broken just for this specific reaction. Hence, it's going to be accurate for this specific reaction. Whereas our average bond enthalpy calculation, as shown here, refers to the making and breaking of bonds when looking at average bond enthalpies, those bonds in many different environments. I hope that's very clear. Let's try another example. Once again, I'm going to give you a few seconds to read the question, pause the video. Once you've read the question, I'll go through my answer. When you're ready, compare your answer to mine and let's see what we did. So, pause the video now. And continuing. So, here we have a compound. Don't worry about what this compound is. It's reacting with hydrogen cyanide to produce this compound. Use the following average bond enthalpy data to calculate the enthalpy for the above reaction. Now, I'd like to appreciate, based on what you understand of how the covalent bonds are made with these atoms, what you think the displayed formula would look like for this. and of course for this, and therefore what the displayed formula for this would look like. Once you've made those calculations, I'm hoping you've had a chance to look at why the value given in the data book for this reaction is different to the calculation above, the average bond enthalpy calculation. Which value is more accurate and why? Well, let's see what answers you came up with. Again, what I've done, my calculation, my reaction, a dotted line, now the displayed formula for my compounds, allowing me to now see the only bonds that were broken. This C double bonded O, which has now become a CC bond, a CH bond here was broken, an OH bond and a CO bond were formed. What I'm hoping you can now appreciate is I don't need to now calculate the breaking of every single bond, which would make my calculation pretty long, and the reforming of every single bond, which again would make my calculation on this side very long. We can just think about the bonds that are actually broken, which was that bond there and that bond there. Even though I've got all the data I need here to do the complete calculation, we can look at a very simplified version, the breaking of one C double bonded O, the breaking of one CH bond. Forming the bonds, a C, OH, and of course this CC bond allowing the cyanide to join the carbon. Calculations as such here. Data taken from this table. Energy going in, energy coming out. Totaling that up, simple subtraction, energy going in minus the energy coming out gives me positive 43 kilojoules per mole, an endothermic reaction. The enthalpy for the reaction, look at the previous video to appreciate what the symbolism means. The enthalpy for this reaction is positive 43 kilojoules per mole, illustrating energy going in to break bonds in the reactants is more than the energy being released when reforming the bonds in the products. Therefore, it's an endothermic reaction. Finally, our answer, the data book value is more accurate as it is a value specific to the bonds in this reaction. That's this reaction here. Whereas the average bond enthalpy calculations, this down here, are for the bonds when considering many different environments. I'm sure you all got the same answer for yourselves. I'll go through more examples in the Q&A video. For now, let's move on to Hess's cycle.
So we're now going to look at Hess's law. The idea that some reactions can be measured directly, others cannot, simply because the activation energy may be too high. Some reactions simply take a very long time because they're too slow, or some reactions simply cannot possibly happen without other reactions happening in between. So you could put 2 reactants or 3 reactants together and a variety of products are going to be created as opposed to just the one you want. I'll go through some specific examples as we go through the next few questions after this. First, the definition. Hess's law. The enthalpy change for a reaction through a direct route is equal to the sum of the enthalpy changes for any indirect route, provided the reactants and products are the same and the conditions are the same. So here, in this schematic, the reactants, X and Y becoming Z, the product, the enthalpy change, which I've labelled as 1 for that direct reaction. However, they could have alternatively become A and B. That reaction would have had delta H2 as its enthalpy change. A and B could then have become Z through a different reaction, delta H3. The idea being, if the starting and finishing reactants and products are the same, and the conditions in terms of temperature, pressure are the same, the direct route, delta H1, is equal to the indirect route, the sum of the enthalpies of the indirect route, delta H2 plus delta H3 in this case. Hopefully this is all straightforward and you've seen diagrams like this represented before. I'd like to go into a practical example using enthalpies of combustion and formation to illustrate how examiners may test this, but also to bring home the message of what Hess's law is all about. So let's first look at these definitions. We've met these in the previous video. Change in enthalpy, the enthalpy change, under the standard conditions for combustion: standard enthalpy change of combustion, energy change associated with the complete burning of 1 mole of a substance in plentiful oxygen under standard conditions. And because they specifically said standard enthalpy of combustion, we need to have quoted the standard conditions. 1 mole is burning in plentiful oxygen. Here's an example. Propane. I'll give you a few seconds. Try to write down what you think would be the equation representing the standard enthalpy of combustion for propane. Pause the video now before I reveal my answer. So, the answer, propane plus oxygen becomes carbon dioxide and water. Because there are 3 carbons in propane, I'll make 3 CO2s to balance the carbons. The 8 H's will balance with the 4 H2O's. That now leaves me with 6 oxygens here, 4 oxygens here, equaling 10 oxygens, for which I would therefore need 5 O2 to balance. Hopefully you all had the same answers. Let's now look at the other definition, standard enthalpy of formation here. The formation enthalpy under standard conditions, the energy change associated with the formation of 1 mole of a substance from its elements in their standard state under the standard conditions, quoted as 298 Kelvin 100 kilopascals. We've looked at this definition in a previous video. Again, in order to make propane, I've hidden the answer. Have a look before I reveal the answer and see if you get the same equation that represents the standard enthalpy of formation. Pause the video here, have a go, and then compare. Okay, so my answer. Carbon and hydrogen are the elements in their standard states. Now this would normally be, say for instance, graphite. Hydrogen is a gas at room temperature and pressure, and they can be used to make propane. Because of the 3 carbons, I need 3 carbon solid here. Because of the 8 H's in propane, I need 4 in front of the H2 to balance it out. So this is a balanced equation representing the delta HF, the standard enthalpy of formation for propane. Now, having understood these particular definitions and what an equation for each of those would look like, let's now look at a typical question. So here, a Hess's Law question could simply ask you, pretty directly, to construct a Hess's cycle using the delta HC, the combustion information in the table, calculating the enthalpy change for the reaction below. And here's a reaction, which, as you've already seen in a previous page, happens to be the formation of propane, 1 mole of a substance from its elements in their standard states. Here's combustion data for carbon. This is specifically for graphite. Hydrogen, combustion of hydrogen, and the combustion of propane. Some of you may already feel confident to have a go at this. Have a go, pause the video now before I reveal the answer of how I would approach a Hess's Law question. So my answer, my routine is fairly straightforward, and some of you may already have come across this if you've been to any of my classes. First, step 1 is to write the equation of the enthalpy change you're trying to work out. Granted, this is the delta HF for propane. I'm going to keep things fairly simple and simply call it delta H1 to illustrate my routine a bit better. First step, the equation you're trying to work out, write it down. It may not always be a formation or combustion, hence I haven't labeled it as such. However, once you've done that, step 2, put the arrows representing the information we're given. So, the combustion of carbon, I'm drawing the arrow away from carbon, because if you remember, the equation for the combustion of carbon would be carbon plus oxygen becoming carbon dioxide. So what you see here is in the combustion of 1 mole of carbon, the arrow points away from what you're combusting, away from carbon. My arrow is going down, away from carbon. Likewise for hydrogen, combustion of hydrogen would be hydrogen plus oxygen becomes water. To balance that, I'd need a half over here. The combustion of hydrogen, the arrow goes away from hydrogen, so it's going away from hydrogen. Same as the combustion of propane. The equation for the combustion of propane had the arrow going away from propane. For these, the products, combust carbon, we get carbon dioxide, specifically 3 of them because they're combusting 3 of carbons. 4 hydrogens combust to 4 H2Os because this delta H1 equation is balanced. The combustion of my products also produces 3 CO2s, 4 H2Os. Straightforward, I hope. So step 1, what you're trying to calculate using Hess's cycle. Step 2, which way should your arrows point? In this case, combustion data shows away from what you're combusting. Put the products of those combustions at the bottom, balanced. And then step 3, put the values for each arrow next to them. So for instance, combustion of carbon, to burn 1 mole of carbon in plentiful oxygen, minus 394. So therefore, to burn 3 moles of carbon, it's minus 394 times 3. Straightforward. This arrow here represents the combustion of 4 moles of hydrogen. So minus 286 times 4. This is where I got my minus 286 from. Combustion of 1 mole of hydrogen. And of course, combustion of 1 mole of propane is minus 2,220 kilojoules per mole, minus 220 kilojoules per mole is this arrow. You don't have to write down the units, I'm simply illustrating. It's the same units as we have here, kilojoules per mole. So each arrow facing the right direction now has a value next to each one. Step 4 is to simply write down my calculation. The enthalpy change 1, this here, is equal to those arrows. If I was walking down, so I tend to, when I do this in a classroom, I use my fingers to simply show how from this starting position I can walk down these arrows and walk up against the direction of this arrow to get to propane. Directly walk across here, or go down those arrows and up that arrow. Well, to go down those arrows, I'm sticking to the way the arrows are drawn. So my calculation is simply the value of that arrow plus the value of this arrow minus 394 times 3 minus 286 times 4. It's these two arrows. However, to get up to propane, I have to go against this arrow. If downwards, it's minus 220. Upwards, it would be positive 220. Adding the 3 arrows together, that's my calculation, and there's my answer. Hopefully you've had the same, if you've had a chance to do this. Go through that routine again, write in the equation step 1 what I'm trying to work out. Step 2, put the arrows in representing the direction of the information I'm given. In this case, combustion data away from what I'm combusting. These are the products of that combustion. Step 3, the value for each arrow written down tidily next to each. Step 4, the calculation for my direct route is simply adding the arrows together. I'm facing the same direction, walking along the same direction for those arrows. I haven't changed the symbols, but going against this arrow, I've changed the symbol. I end up at propane. Down there, up there. Straightforward. Gives me this calculation and this result. Okay, let's look at a couple of questions that may come up. So here's an example of a question that's fairly typical, just like we saw in a previous example, of what you may see in an exam situation, simply by constructing a Hesss cycle using the enthalpy of combustion data in this table, calculate the delta H formation, enthalpy of formation of ethanol. Now here's an equation representing the formation of ethanol, elements in their standard states, balanced to form 1 mole of ethanol. These are the combustion data. Pause the video now, have a go yourself, and then compare it to the answer I'm about to reveal. So my answer. Step 1, I wrote down the equation I'm trying to work out. Step 2, I put down the arrows representing what information I'm given, combustion data for the combustion of carbon, combustion of hydrogen, giving me 2 CO2s, 3 H2Os, combustion of my product ethanol, arrow going away from ethanol, also giving me the same. So that's all complete now, my Hesss cycle. To this, so that's the arrows with step 2. To this, in step 3, I then added the value for each arrow.
minus 394 times 2, value for that arrow, combustion of carbon, minus 286 times 3, the value for the combustion of hydrogen arrow, minus 1400, the value for the combustion of ethanol arrow. Step 4, I did my calculation. My direct route, enthalpy of formation for ethanol, is equal to the arrows added together, down that arrow, minus 394 times 2, again following this arrow, minus 286 times 3, but for this arrow, I'm going to be going against the arrow, so I change this to a positive 1400. These three, the brackets removed, is simply going to be that. That simple arithmetic brings me to minus 246 kilojoules per mole, not forgetting the units unless they're written on the exam paper already. Hopefully you've done something similar. I do note that in some textbooks and classes, I appreciate this is taught if you're working out using combustion data, as you have here in this example. You could say the enthalpy change for what you're trying to work out is going to be the sum of the enthalpies for combustion of your reactants minus the sum of the enthalpy or enthalpies of combustion for your products, i.e. my reactants minus the product, which in this case a minus of minus would have been a positive. So it would have been the enthalpies of my reactants, these two arrows, as they're written, so they didn't end up with negative numbers as you can see, minus my enthalpy of my product, which in this case would have been a minus 1400, minus 1400, this area here, would have converted this to positive 1400. So although this, if it's stuck in your head and you feel it's working, stick to this routine, no problem. Otherwise, I feel this process that I've outlined, step 1, step 2, the arrows, box at the bottom, step 3, the value for each arrow, and step 4, simply just looking at which direction you're headed, down those arrows, up that arrow, write down your sums, put them down, and add them together. Is a straightforward way that we can then apply to any scenario. So for instance, this was working out the formation of a particular substance, ethanol, using combustion data. Let's look what happens if we're using formation data. So here we see an example of a question where using this formation data, you're being asked to calculate the combustion of ethanoic acid. Now this time I haven't given you an equation. Pretty typical. Sometimes you're given a question where one of the marks is to write down the equation, or they're expecting you to, maybe at a higher level, having realized you do need to have that equation. So I'll give you a moment before I continue talking and show my answer to try this for yourself. Pause the video here, and then I'll reveal my answer. Okay, my answer. So, as I did earlier, I initially began step 1, the equation of what I'm trying to work out, the combustion of 1 mole of ethanoic acid, in the presence of plentiful oxygen gives me carbon dioxide and water. To balance this, 2 carbons give me 2 CO2s, 4 hydrogens give me 2 H2Os. Overall, the oxygens on my right-hand side were 4 plus 2 is 6. There's already 2 oxygens here, so I only need 2 O2s to give me 4 oxygens from here. My oxygens are balanced. I'd like to mention at this point the idea that if you're having to combust ethanol, ethanoic acid, alcohols and carboxylic acid, which already have oxygens, or other compounds such as esters, which may have oxygens in, be careful how you balance this part for your equation. You'll have the oxygens from carbon dioxide and water. When you're combusting alkanes, as we saw earlier, you simply balance those oxygens with this oxygen on the left, reactants. But if you've already got oxygens in this reactant, such as ethanoic acid or ethanol alcohols or carboxylic acids or esters, you need to be aware to consider those oxygens when trying to balance these oxygens here with your products. Hopefully I've not confused you. Be careful when you're balancing equations when combusting non-alkanes and alkenes, i.e. those that contain oxygens, esters, carboxylic acids and alcohols. Anyhow, first point, the equation I'm trying to work out. So, in step 2, arrows pointing towards ethanoic acid, carbon dioxide and water, because I've been given formation data. Therefore, the formation of ethanoic acid, arrow would point towards what I'm forming. Formation of CO2, as illustrated here, carbon plus oxygen becomes CO2. Forming CO2, the arrow points towards CO2. Arrow points towards H2O. Hydrogen plus oxygen gives me H2O. Here's a balanced equation. Arrows pointing towards H2O. Towards H2O. Now, what's also worth noting is the formation of CO2. This equation is the same as the combustion of carbon, which you may remember from a previous question that we just looked at. Likewise, the formation of water is the same as the combustion of hydrogen. So worth keeping in mind, if ever you're given the values formation of CO2 or the combustion of carbon, you're trying to put the arrow pointing away from carbon towards CO2. Likewise, formation of H2O, combustion of hydrogen, the arrow is going away from hydrogen towards H2O. In this case, formation of CO2, arrow is going towards CO2. Formation of H2O, arrow is going towards H2O. Formation of ethanoic acid, arrow goes towards ethanoic acid. 2 carbon solid, 2 hydrogen gases, and 2 oxygens from this pile here produces my ethanoic acid, but I haven't put an arrow going to the oxygen, simply because oxygen gas, to become oxygen gas, does not need energy input. Therefore, there's no enthalpy change and is not worth putting into the Hesss cycle. But to balance this box at the bottom, I do need to include those oxygens here. So 1 pair of O's were used for ethanoic acid. The other 2 O's, oxygen molecules, were used to balance these oxygens here. Now, 2 CO2s, 2 H2Os. If you add up those elements, you would also need the exact same amount because this top equation was balanced. Having now completed the arrows with the box at the bottom for the elements from what I'm forming my reactants and products, step 3 is to put the values for each of those arrows: minus 483.5, minus 394 times 2, minus 286 times 2, based on the values I was given up here. My calculation delta HC combustion, the direct route, is equal to, now this time from here, reactants to products, I have to go down this arrow, positive 483.5, up those arrows, so therefore the values are as they are, minus 394 times 2, minus 286 times 2, add the 3 together, they're the numbers, that's my final answer. What I'd also like to appreciate at this point is the idea that I came down the arrow and went up those arrows. This brings us to another formula you may have seen in your own notes, where if you're using formation data, the enthalpy you're trying to work out for the direct route is equal to the sum of the enthalpy formation changes of your products minus the sum of the enthalpy data or formation of your reactants, which is simply just that data as it is minus that data, the formation of your reactants, H3.5. Because it's minus of that, we end up with a positive value as we looked at the calculation. So the enthalpy changes of your products minus the enthalpy changes of formation of your reactants. Yes, if you're comfortable with that formula, use it. Otherwise, my calculation is very straightforward. Go down that arrow, up those arrows. I hope that makes sense. So moving on, You could have a question where you're trying to work out the enthalpy for a particular reaction, the enthalpy change for a particular reaction. You're given formation data. It could have equally have been combustion data, but it's not a combustion reaction, it's not a formation reaction, it's simply just a reaction. What I'd like you to do, pause the video, have a go yourself, and after a few seconds I'll reveal my answer and you can compare to see what you've done. So my answer. Sticking to my routine, my step 1 was to write down the equation of what I'm trying to work out. Step 2 was to put the arrows representing the information I'm given, formation of my reactants, H2O, formation for ethanol there, arrows in the right way. At the bottom, because it's formation data, I have the elements required to produce my reactants and products. Here you can see. Finally, step 3, the values for those arrows forming ethene plus 52 kilojoules per mole, forming a mole of water minus 286, forming a mole of ethanol minus 278. My delta H of reaction, I'm going against that arrow, I'm going this way. So I'm going to go against that arrow, minus 52, against this arrow, positive 286, up that arrow, minus 278. Add the 3 together, straightforward, there's my calculation. You may have used your own for the formation data, which was products minus reactants. You would have ended up with the same answer. Whichever method is easier for you. Have a go. So what I'll do is address some exam style questions later once I've had a chance to finish the energy module 3 revision.